Alright, hello again, this is Jeff Scott. I've been giving you a detailed overview of the Microsoft Security Development Lifecycle, or SDL. We've been talking about the education and awareness, and we've gone over several things, and I've broken this down into at least 2 lectures. There are 204, I believe, total slides, so I went through the first 91, and that was part 1. This is part 2. And in part 2, we're going to begin by talking about, as you can see here, buffer overruns. All right, it's not my goal here to sit and read slides to you, but the idea, when you start talking about buffer overruns, the idea is you've got a buffer, which is an area in storage that you allocate that's a certain size. When you've got a buffer overrun, you attempt to put more data into the buffer than the buffer can hold. It's the old proverbial trying to stuff 10 pounds worth into a 5-pound bag. Now they talk about the 3 areas of memory right here. The first, as you can see, is the text segment, also known as the code segment. All right, that's where the compiled code of the program will be. It's the machine language representative of the program. So in other words, it's the zeros and ones that the program needs in order to be able to do what it has to do. Next, you've got the stack segment, and as mentioned, that's where your automatic variables are put. Automatic typically means local variables. All right? A stack is a last in, first out, or a LIFO type of storage device. And the way that that is typically explained is if you think about, if you go to a cafeteria and you've got a stack of trays, typically the next person in line takes the top tray. So the last tray that was put into the group of trays is the first one that'll be taken out. You also have the heap. Whereas the stack is used more for local variables, the heap is used for global variables and for static variables. Now, just so you know, when you start talking about this stuff, it's normally stack overflows that are the most prevalent. I don't know if I've ever heard of a text segment overflow, buffer overflow, but heap segments can happen. All right, we'll talk about all those in later lessons. So as it says, typically what you want to do as an attacker is to corrupt the execution stack of an application. What that means is rather than having the program go through and do whatever it's supposed to do in steps 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for example, what will happen is it'll start to go through its regular steps, and then the attacker can cause arbitrary code to be executed. And in that way, it's possible for the attacker to take over the machine itself. And they mention here that this can be prevalent or present in a web server, and basically it can be present anywhere. Now, you had a much better chance historically of having problems with buffer overflows with non-managed languages such as C and C++. With newer, more managed, so to speak, languages, those in the .NET framework, so Visual Basic .NET, C#, etc., and Java, it's harder, though not impossible, to have a buffer overflow. And they go through some stuff here. And again, these are just examples. There are more ways than this that you can have buffer overflows. Notice as it says, these types of attacks generally rely upon 2 different techniques, usually in combination with one another. Writing data to a particular memory address and having the operating system mishandle data types. Whoa. As it says, this means that strongly typed programming languages that disallow memory access usually prevent buffer overflows from happening. Well, what does that mean? Well, if you've got a language like JavaScript or PHP, those are loosely typed, because with both those programming languages, you basically the system figures out the type of data the variable is at runtime, and you can change it on the fly. But with strongly typed programming languages like C, C++, C Sharp, Java, Visual Basic.NET, all right, you have to say, for example, int age. And when you do that, age can only hold a whole number, and you can't change its data type while the program is running. Now that says it usually prevents buffer overflows from happening, but not necessarily. So again, the author says almost every platform with the following notable exceptions. This isn't really true, because it is possible to have a buffer overflow on any strongly typed, loosely typed, managed, unmanaged, .NET, non-.NET platform. As mentioned here, managed code is the term coined by Microsoft to identify that code that will execute only on what's known as the CLR. The CLR, or Common Language Runtime, that's Microsoft's version of the Java virtual machine. So again, managed code is typically the newer code, unmanaged is typically the older code. I put this in here. I literally took this from online someplace. I copied it to a spreadsheet and then threw it in here. But the key things to realize when you look is C and C++ and assembly. All right, strongly typed, no. Memory access, yes. Unsafe. All right. Not sure what that one was supposed to be honest with you. Oh, that's safe or unsafe. So the only two that are in here are deemed as being unsafe are C, C++, and assembly. Although, again, it is possible to get a buffer overflow under any platform. So how do you try to prevent it? Well, you want to look at your code. You run a combination of automated tools and manual tools, because there are some that are designed to flag code that could potentially come up with buffer overflow errors. You train developers. You have non-executable stacks, and there's a hyperlink here if you're interested more on that. Again, you use some of the compiler tools. You use the safe functions. Now, even those Microsoft, for instance, not only is there strncat and strncopy, there is strcat and strcopy. The N that you see in both of those, right in the middle, all right, that stands for basically number of bytes that you want to copy. And to my knowledge, and I could be wrong on this, but I know Microsoft, the strcat and the strcopy, Microsoft has deemed those to be illegal, and they're not allowed in any new development. And the idea is over time, they'll be removed from any legacy code. But I do believe they don't like you to use strncat and strncopy either, just because of the fact that even though they're more safe, it's still possible that you can have buffer overflows with them. Make sure that you have your machines fully patched, and periodically scan your app with one or more commonly available scanners that look for buffer overflow flaws. All right, as mentioned, stack overflows are the best understood, and that's typically they're best understood because that's where most buffer overflow attacks occur. So as mentioned, there's two types of buffers: a source buffer with arbitrary input from the attacker, and a destination buffer that's too small to hold that. The second buffer resides on the stack, and it's pretty close to, if not directly, connected to the function return address on the stack. As mentioned, the faulty code does not check that the source buffer is too large, and it copies the information into it, which is fine until it gets to the end and it still has stuff to copy, so it overwrites whatever's next to it. Again, those could be operating system instructions, those could be anything. When the function returns, as mentioned here, the CPU unwinds the stack frame and pops the now modified return address from the stack. Control does not return to the function, rather the machine is now under the control of the attacker. All right, just a simple example of this where, again, the idea is you've got a buffer, of size 10, and notice what we're trying to put in here, something closer to size 20. How to see if you're vulnerable? Again, you're more apt to be vulnerable if you use one of the older type of languages that uses unmanaged code. If your program copies data from one buffer on the stack to another without checking size limits first. If your program does not use techniques such as canary values to prevent buffer overflows. A canary value, for lack of better words, in some languages it's kind of called a peak, so it's a look ahead type of thing. So you want to make sure that as you're copying stuff in, once you get to the end of the buffer you're copying to, if there's still stuff to copy, you don't want it to continue. Again, we'll talk about this in much more depth and breadth of coverage in some of the other later lectures. Deploy on systems capable of using non-executable stacks, and I gave you a URL for that earlier. Again, use higher level programming languages. Validate all input. If you rely upon the operating systems or utilities, ensure that they adhere to the principle of least privilege. Ensure that they, as much as possible, protect against different types of overflows, and ensure they're up to date in terms of their patches. Other types of buffer overflows include format string overflows or format string vulnerabilities rather. As it says there, basically they take advantage of the mixture of data and control information in certain functions, such as C and C++ is printf. And printf historically is one of the most insecure functions there is. So there's the example. What they're saying here is this will work fine if you say printf %s str, because str has been defined up here to be a string. But if you remove the %s and you just print out str, it's possible that that could be exploited. And again, these are the kind of things where developers historically, they might be lazy, they might be in a hurry or whatever. Sometimes they don't do everything they should do to help secure their code as much as possible. So if your program uses printf or sn printf directly, you might be more vulnerable. If the program allows functions that allow input from a user, you might be more vulnerable. Sometimes you can't get around this, but you're trying to protect yourself as much as possible. We already talked about using the higher level programming languages, validating input, and avoid using functions such as printf whenever possible. You've seen this before. If you're relying on the operating system, make sure that you adhere to the principle of least privilege, use compilers that help protect against stack and heap overflows, and be current as far as your patch management. Next are integer arithmetic errors. The best way to explain this, and you can see the example right here, but there are several different data types that deal with whole numbers. One of them is type byte, and byte has a valid range of 0 to 255. But imagine what I was doing is I was trying to add two people's ages, or let's make it easier. Let's say we're going to add the ages of 3 people. All right, and let's suppose that each one of those people were in their 90s. So let's say they're all 90. So I add 90 and 90 and 90, and I get 270. 270 is of course bigger than 255. It's very similar to the example right here. What we're trying to do is we're trying to add together 192 and 208. And what ends up happening is we're trying to shove it into a variable that won't hold all of it, so the result won't fit into the 8-bit result set. So what we get, as it says, if your application doesn't check for such an exception and take proper action, it'll say things like 192 plus 208 equals 144. Notice I bolded this. This type of overflow can occur on virtually any type of platform, so it's not specific to .NET or whatever. You can use it in Linux, Unix, Starnix, Mac, etc. How to see if you're vulnerable? Examine the use of signed integers, bytes, and shorts. See if there's any cases where array indices can be out of line. How would your program react to negative or zero value for integer values, especially during array lookups? Back in the day, we're not talking that long ago, maybe 10 years ago, VisualBasic.net did allow for negative indices in arrays. .NET has developed this safe int class. All right, I'm not going to bring that up, but the idea is it allows conversion between different types of whole number variables. If your compiler supports the option, change the default for integers to be unsigned unless otherwise explicitly stated. Use unsigned only or whenever you don't need to worry about negative values. Use range checking. If you're using one of the newer languages, check for exceptions. All right, let's jump into cross-site scripting next. As mentioned here, cross-site scripting, which is typically referred to as XSS, they're a type of injection. Notice they typically occur when an attacker uses a web app to send malicious code. An attacker sends the cross-site script to via some type of malicious script. The end user has no way of knowing that it's malicious. They click on a link or whatever, all right, and bad things can potentially happen. Now, before we go through this, let me just say that some of these attacks, as time goes on, are getting smarter and smarter, because in the quote olden days, like a couple years ago, whenever this kind of attack happened and somebody sent you a link, you'd have to click on it for something to happen. Now today, people have gotten smart enough that they can actually put malware into mouse over events. So all you have to do is mouse over a link and it's possible that your machine can become infected. Everything that you see in here goes back to untrusted data and validation. Again, never trust data, always validate. Even more. Some of this stuff like HTTP only cookie flag, etc., using the XSS protection as response header, we'll talk about that as we go on. Okay. All right. Closely related to cross-site scripting is cross-site request forgery, or CSRF. Notice it's a type of attack that occurs when a malicious website or something similar to that causes a user's browser to perform an unwanted action on a trusted site. They're caused when an attacker tries to, or it succeeds, I guess, into making a target system perform via the target's browser without the knowledge of the target user. So the user machine does something with the machine that they didn't want it to do. Notice this can happen even with strong encryption, so even with HTTPS, I should say. What doesn't work for trying to fix this? Some people think, well, I'm going to have a secret cookie, and I'm going to submit that, and that'll solve the problem because I'll put the extra information in there. That's not right, because all cookies are submitted with each request. All right, whether or not the user was tricked into submitting the request is irrelevant. Only accepting post requests. So in other words, not even allowing gets. As it says, there are numerous methods in which the attacker can trick a victim in submitting a forged post request, just like a get. Multi-step transactions, they don't work either unless you've got something with multi-step. If the attacker can figure out that things happen in a lockstep type of way, they can predict or deduce what's going to happen next. So again, it will still be possible for a cross-site request forgery to take place. URL rewriting. The idea is you don't put all the information into the URL, so the attacker has to guess. All right. But that may or may not be important because, as mentioned, the user's credential is exposed over the URL. So if I can become the user, all right, and do, for example, session hijacking, it's not going to matter because I've got complete control anyway. So what does work? A synchronizer token pattern. And again, as you can see here, I've put in a URL, so if you want to learn more about this, you'd be able to. Notice this requires generating a random challenge tokens that are associated with the user's current session. So the idea is, even if things are going to go lockstep, you're going to have something where you've got some kind of a random value that's going to make things at least appear to be a little bit out of the norm, and that random value will be difficult, if not hopefully impossible, for the attacker to deduce and be able to break in and create a CSRF. Things that you can do, and this should just be normal types of stuff. Log off immediately after a web app. Don't allow the browser to save usernames and passwords. Don't even put a remember your login on there. Don't use the same browser for sensitive applications that you use for surfing the net. Use plugins like NoScript, and again, as you can see, I put a URL there, which makes post-based CSRF very difficult to exploit. Again, you'll notice with all this stuff, we're saying very difficult. We're not saying impossible because, as mentioned several times in these lectures, there is no silver bullet. So as you can see, the difference between CSRF and XSS is that XSS is designed to exploit the trust the user has for a site, and CSRF exploits the trust that a website has in the user's browser. All right, from cross-site scripting and cross-site request forgery, let's go into the land of SQL injection. It's another injection type of attack, and as mentioned in the bottom bullet there, they're a type that's used where SQL commands are injected into input in order to do and run certain predefined SQL commands. They allow attackers to spoof identity and tamper with existing data. And the key thing is, as far as the tampering, they can remove tables, print out the values of tables, change the values of tables, etc. In the worst case, as mentioned here, they can destroy data or make it otherwise unavailable and become system administrators or database administrators. This is what I read online as far as where it's common. Again, it says ASP.NET, most of the .NET languages, and Java are less likely to have easily exploited SQL injections, and that's true. But again, that doesn't mean it can't happen. It means it's harder for it to happen. Here's the problem. As mentioned right here, the severity of an SQL injection attack is limited only by the attacker's skill and imagination. It's typically considered to be a high impact severity. Here's some examples, and let's take a look at and jump into it a little bit more. Let's see. Oh, well, what we have in here is we're hard coding a value in it. If people, if you can get a hold of that, you can do damage. Well, how do you keep from getting a hold of that? All right. As it says, that example is unsafe because it would allow an attacker to inject code into the query because the customer name that's right there is not validated. So what you use typically are what are called prepared queries, and what that means is you put a question mark in there, and at runtime you'll pass information into the system, but that information that gets passed in will automatically be validated to make sure it's of the right data type, of the right size, etc. So as mentioned, parameterized queries first force the developer to define their SQL code and then pass each parameter to the query later. You can see it right there. It's an ampersand, no, not an ampersand, an @ sign is used in some languages also. It varies based on the language. Not only are there prepared statements, but there's also stored procedures. I've always defined a stored procedure as basically being a saved query. So it's something that you've run, something that you trust, and you basically save it. And as it says, the good news is that's the norm in most stored procedure languages. You build SQL statements with parameters, which are automatically parameterized unless the developer does something out of the norm. So you end up with something like this. Notice the @ sign in this case. And it's inside of a try-catch block for even more security. All right, so how do you try to defend against SQL injection? Well, number one, there is to escape all user input, especially databases. Quite often when you have to use certain languages, when you want to put something into a database, you have to put it within single quotes. The problem is if you put something within single quotes and you've got a last name, let's say that it's O'Hara, where it's O followed by a single quote, H-A-R-A. That can screw the system up, but there's ways around that also. So we've talked about prepared statements, stored procedures, escaping all input, also using the theory of least privilege. Notice what it says there in the bottom bullet. Do not assign DBA or admin rights to application accounts. Start from the ground up. Determine what access rights the accounts require and give them just that, no more. Remember, it's always possible as an administrator that if someone temporarily needs an upgrade in their access rights, that you can give them that temporary upgrade, let them do what they have to do, and then downgrade them again. In whitelist input validation, the thing with whitelist, what you try to do with whitelist is you try to show every valid possible input. All right, and you only allow those. The problem with whitelisting is quite often you can come up with something that's valid even though it may on the surface look invalid. If you want a little bit more information, there are some really good cheat sheets out there. Okay, and I've linked to one of them here. All right, let's talk about cryptographic designs. It says there a cryptographic system can only be as strong as the cryptographic algorithms, etc., hash functions that it relies on. Well, the good news is most of the stuff that's out there, that's been out there for a while, is tried and true. And most of it that's been out there for a while that's not tried and true, Microsoft recommends that you don't use it anyway. So they've got different types of cryptographic algorithms that they say you can use and certain other ones that you should avoid. As it says, many systems fail because of mistakes in implementation. Some systems don't ensure that plain text is destroyed after it's encrypted. And plain text means basically if I send something over the wire and I'm sending my name, it just goes over there as Jeff Scott. It isn't at all encrypted. Many systems break because they rely on user-generated passwords, and as mentioned, left to their own devices, most users will not create very strong passwords. Some systems, particularly e-commerce, rely on tamper-resistant hardware, smart cards, etc., which may assume that who's ever using it is always valid and should be able to use it, but may or may not indeed. Many computer systems make poor trust assumptions about the computers on which they run. They assume that the operating system will handle it and everything will be fine, for example. Even when a system is secure, the users may be able to subvert it either by accident or because they're malicious. As it says, the classic example is the user who gives their password to one of their co-workers so they can fix some problem while they're out of the office. Stuff like that does happen. Strong systems are designed to keep small security breaks from becoming large ones. All right. Sometimes products get the cryptography wrong. They rely on older cryptographic algorithms that are very weak. Other times, what ends up happening is places think that they can use their own cryptographic algorithms, or they write their own, and that's typically a bad idea also. So most of these systems, as mentioned on the slide here, rely on prevention as their sole means of defense. As it says, the cryptography is designed to keep people from cheating, lying, or whatever, but you shouldn't be that narrow. A strong system also tries to detect abuse and contain the effects of any attack. Again, sooner or later, every system will be attacked. So it's important to detect it and then try to mitigate the damage as much as possible. A good system must defend against every possible type of attacks, even ones that aren't known about. You know, as they say in here, attackers have as many chances as they want. You may have only one chance when you're trying to go through preventive mode. As mentioned, interpreters are trendy. There's not a whole lot of stuff that's out there. So if you've got a language that's interpreted, they may be a little bit more apt to be attacked. Sorry. Grab that. Worse yet, as mentioned, they're less protected than most compiled programs. Okay, there's not a lot of stuff out there. There's not a lot of documentation out there on interpreters. All right, security testing versus functional testing. Functional testing, as mentioned here, involves the app testing the app against business requirements. You want to make sure that it behaves the way it was designed to behave. All right. As it says, it ensures that the software is ready to release to the public, and it verifies that all the requirements have been incorporated. There's positive functional testing and negative functional testing. With positive functional testing, you put in valid inputs, or what you expect to be valid inputs, to see if the system responds accordingly. With negative functional testing, you put in invalid types of inputs, and again, see that the system will at least handle it. Non-functional testing, they mentioned there, is designed to figure out if the product will have a good user experience. And if you haven't heard the term UX yet, it's getting more and more popular. So many websites that sell similar products are so similar that sometimes the only way to get a person to your site is to try to maximize their user experience. Make it as simple for them to use, make the site as aesthetically pleasing as possible, etc. Types of non-functional testing, there's a couple. Some more. All right. So as mentioned here, functional testing ensures that the product meets the customer's business requirements and doesn't have major bugs. It's designed to determine that the app's features and operations perform the way they should. In other words, that it behaves correctly. An app needs to pass both categories, not just functional testing, but security testing, to make sure that it does what it indeed is supposed to be doing. Organizations may have to do this for legal reasons as well. And why else would you want to do it? Well, adding security usually does involve additional expense, but in the end, it typically does not. It should increase productivity, breaking barriers, but the other thing is, going along with this, and I don't know if it's one of the ones that's in here or not, but it's goodwill. It helps your reputation. Allows you to do self-analysis, communicate to your customer. Okay. Let's talk a little bit about risk assessment and the difference between quantitative and qualitative risk assessment. In quantitative, as it says, the likelihood of occurrence of particular threats and risks and loss associated with these are estimated according to predetermined metrics. With qualitative, it's more common. All right, the assets are discovered and reviewed for known vulnerabilities. Then they're measured against some kind of a scale to determine the probability of that being exploited. So quantitative yields results in terms of financial impact. The stuff as mentioned is expressed in monetary values, percentages, probabilities. All right, it allows for more control, but it can be time sensitive and it can be expensive. So most people do the qualitative because, as mentioned there, it requires less time, it's less costly, it's quicker to process, and it's simpler to do. Here's part of the problem. Vulnerabilities are rated subjectively. Anytime you bring a human element into it and make it subjective, it makes it harder to guarantee that indeed you're doing exactly what you want to do as opposed to doing something that's objective. Here's some typical public employee data, some typical private restricted employee data, and some highly restricted employee data. Now, not every agency agrees with this, all right, but this is some stuff that I found online. So as far as best practices, as we're coming to the end in here, enforce effective password management policy, use least privilege user accounts, harden your client devices by deploying multi-layered firewall protections, conduct regular pen tests and vulnerability scans, require email authentication on all inbound and outbound mail streams, continuously monitor in real time the security of the organization's infrastructure, deploy web app firewalls to detect and prevent common web attacks like cross-site scripting. Here is a URL for some stuff in here on, as it says, for Gartner's top security trends and takeaways. So a lot of this will be repeated in there. Permit only authorized wireless devices to connect to your network. So have some kind of policy for that. Implement always on secure socket layer. All you're trying to do is, again, you're trying to decrease the chance that you're going to be hacked. Review server certificates for vulnerabilities and risks of the domains being hijacked. Develop, test, and continually refine a data breach response plan. Finally, to summarize, just a couple slides, learn from your mistakes. Minimize your attack surface. Use defense in depth. Use least privilege. Employ security defaults. Backward compatibility can be tough. Assume external systems are insecure. Plan on failure, but plan to fail to a secure mode. Remember, we talked about this in an earlier lecture. Security features do not necessarily equal secure features. Never depend on security through obscurity. In other words, whatever you're doing for security is going to have to be made public or at least semi-public. Don't mix code and data. Fix security issues promptly and correctly. All right, these are other things that we're going to be talking about. So that's it for this particular presentation.